All right, afternoon. Okay, so we were working on regression, and we're going to keep working on that today. First, I have some comments, though. One is about the assignment. Another one is a little bit about sort of a meta discussion about what the class is supposed to be about, that I think there was a little, what we're really... I'm going to throw that on the floor just a second. All right, let's try this again. So to start with the assignment 5, we talked about vector quantization. With vector quantization, there's actually two methodologies that you can use to create sort of the fingerprint. I described one of them in class, and the book discusses the other one. They work essentially the same. They're just there's a slight trade-off. So if I have some waveform, I'm low on paper today for some reason, so I'm going to try not to use too much paper. If I have some waveform, and I want to do vector quantization on that, I can do one of two things. I can say this vector, this is some length, and I'm going to cut it up into equal-sized pieces. And then I'm going to use the clustering method to get those pieces out, to match those pieces up and make a fingerprint. That's a perfectly good way to do it. That's what the book recommends. That is what the assignment recommends. That is not the only way to do it. The other way to do it is to take random windows. So instead of sequential windows that are all piled up together, you could just take random windows. So you can come along and you can say, I'm going to take this window, I'm going to take this window, I'm going to take this window, and this window. So there's sort of a stochastic process going on there. They both work. There's nothing wrong with one or the other. There is generally just a performance versus accuracy trade-off. The stochastic version will generally generate less samples. If we think about the image example I showed you guys, the images were very regular. They had a very repeating pattern. And so I think I took something like 15 samples of 10 by 10. So I took a very small number of random samples to get the fingerprint. If we were going to do it with the sequential version, we'd have to go over the 600 by 600 image, cutting out little plots of 10 by 10. So we'd end up with 4,000 a little less than 4,000 things that we needed to cluster to figure out where the clusters were. So there's this trade-off of how many segments you're going to generate versus how much coverage you're going to get of the space. Now, if the image or the signal is very regular, we don't need all these extra these things that are all sequential. If there's a lot of repetition in this pattern, you need a much smaller number of those. So that's sort of the trade-off. So you could do it either way. I generally think of it as being the stochastic random way, but it certainly works just fine to do it the sequential, just cut it up into however many pieces, and then normalize so you only have, once you get the cluster, you normalize so it all adds up to 1. So either one works. I think we put out a Piazza post on this, so if you didn't understand what I just said, you can read the Piazza post. I don't know that it has any more details, but it might give you a little clarity of what we were asking. The second thing that I wanted to talk about just a little bit really quick is sort of the point of this class. And maybe I should have talked about this a long time ago, but this came up in a TA meeting the other day when we were trying to design some of the homeworks. And in this class, we talk a lot about the different tools that you have available in machine learning. We talk about different ways to do classification, different ways to do clustering, different ways to do regression, and then we're going to talk about a bunch of additional tools later on to do very different ML tasks. these tools are things that we have to teach you. You have to know what's available. But when you get into actually doing applied ML, the tools are the smallest bit that you're going to be doing. I mean, if you're using sklearn, usually any one of our algorithms that we talk about is going to use 2 to 3 lines. And those 2 to 3 lines are just going to be, you look up the sklearn docs, it'll give you an example at the bottom, and you put those things in and it spits out an answer. And now you have to know how to interpret that answer, but the real work in machine learning, the real work for a data scientist isn't running the algorithms. That stuff's easy. The real work is getting the data formatted, figuring out what features to use, figuring out what's in the data, when there's mistakes, when there's errors, and then putting it all together in sort of a pipeline of processing all the data, taking it step after step, using multiple tools to get the answer that you want. And so in an applied class, we really want to teach that sort of step by step. The homeworks are really designed to get you to think about what does it take to do sort of a pipeline of data. Homework 5 specifically was designed to do this. You have to cut things up, you have to do some clustering, and then separately you have to cut things up again and figure out what the clusters are and then build a classifier based on that. That is very much what ML is about. That's what, if you get an ML job, that's what you're going to be doing. You're not going to be just going, I'm going to do linear regression and have some magic happen. You're going to be transforming the data, processing it, trying different things. There's this very interactive process to do ML. And the tools that we're talking about and that you need to know about are actually the smallest real bit of work. I would say that like 95% of the work I did in ML was building pipelines, transforming data, moving things about, looking at data, and then about 5% was actually, let's do linear regression on it. That's automatic. Once you decide you have the data and you want to do linear regression, you just do it, and it spits out an answer. Now you have to double check the answers. You have to know what it's doing and whatnot. But I just wanted to make that point that, that's what you should take away from this class. That's what you should hopefully get out of this class, is that there's a lot of pipelining, there's a lot of work with data, there's a lot of transformations. And that's what we try to teach in the homeworks more than what we teach in the class. It's a hard thing to teach until you just go and do it and you experience it. That's the hardest part, is you can't teach people how to go step by step through a pipeline. You have to do it to get a feel for how this stuff works. Any questions on that? I don't think there's a big discussion to be had there, but all right, so we talked about some text processing last week, and I just wanted to give a quick demo of some text processing here. What I did was I took our text of our book, and I just found a PDF utility that dumps basically all of the text into a text file. It's just, there's tons of garbage in there. It takes figures and mangles them, and just puts text everywhere randomly. So it's a very dirty, messy data set. However, I did that, and I'm just going to step through here. So there was, after I got rid of like some periods and certain junk, there was about 200,000 words in our textbook. And then what I did was I chopped it up by page, which was actually kind of a pain because I just had to look for the page numbers that got dumped. And there was 440 pages over the course of 22 chapters, and there was about 1,200 unique words after I got rid of lots of garbage, the stop words, anything. Basically, I kept any word I think that was 3 characters or longer, got rid of all the stop words, did all sort of that stuff. So it came out to be 1,200 unique words, which is actually, given how big language is, 1,200 unique words in the book is actually tiny. That's a very small corpus. You can think of most corpuses being 10,000 words or more. the English language is generally, it's hard to determine exactly how many words there are, but it's generally, the ballpark is about 1 million words. And if you have a really good vocabulary, you might know 200,000 of them. So it's actually, the English is very big. Now, most of those words we never use, and they're very rare and stuff like that. But 1,200 words is actually a really small number of words. And I didn't stem these words. So things like cluster and clusters actually count as 2 different words. So you don't have to have a very good vocabulary to read our book. So let's see. Then we talked about doing IDF. So first thing I did is I looked at the word frequencies. This is very much what you would expect. The green line is the word frequencies, and then these are just ordered by the number of occurrences. So the green line, you can see it's a very long tail distribution, meaning there's a lot at the front, and then the tail gets down to just a couple references. Another thing is I got rid of any word that occurred less than, I think, 3 times. So actually there's more than 1,200 words, but there's a lot of words that just never are used. They're really rare. Then I adjusted this by IDF. And so the blue dots are the same words. They're ordered in the same way as the green line, but there's an IDF adjustment that should prop up the rarer words and downweight the more common words. Now, it didn't do a very good job on this. You'll notice that it actually propped up some of the very common words a little bit, which we generally wouldn't want. You could play with the IDF formula to reduce that a little bit. Like we could add a little bit of a prior that'll push some of these things down. It doesn't really matter, but in general it did what it's supposed to do in that it took this very curvy sort of thing and then sort of flattened it a little bit. That's what we really want IDF to do. I then plotted this is basically what oh, there we go. This always comes out to a weird spot. I then plotted I took the word vectors and shrunk them down to 2 dimensions using something called TS&E. TS&E does the equivalent thing as MDS. It just does a better job of it. And we're going to talk about TS&E later on in the class. It happens to need to understand it, you need some mechanics that we don't get to until a little bit later. So, but TS&E versus MDS, they're both in scikit-learn. You can look at one versus the other. It doesn't really matter. For our task, this one makes a better cloud, whereas MDS had a tendency to put everything right in the center with only a little, a small number of outliers. Just like we did in the book, we can look at, for each of those quantiles, we can divide this up into 3x3 grids, and we can look at sort of the different quantiles. And you could kind of look at this and kind of guess what chapters these might kind of go with. So this is our clustering, probably our EM chapter. This is another clustering one. I'm not sure what patches and signals go to. Nodes and columns, those are just weird junk words mostly. Logs and images, I'm not sure what that one went to. Here's the classifier sort of stuff. Here's the nearest neighbor classifiers probably, or possibly this is all the way back into it has some bleed over from the neural nets. There's nothing that's forcing, the pages from a given chapter to be in the same quantiles. So you get kind of a mess here. But we can go on, and we talked about doing just a nearest neighbor search, where you take the whole document vector, all the documents, all their word vectors, and you can just do a cosine distance to do a search of all the documents. So what I did here was I grabbed the decision boundaries. I searched for decision boundary. This was my input. And here's what it came up with. So it came up with a chapter that had to do with SVMs and random forests, where we talked about decision boundaries. It came up with another page inside that, another page. This happens to be the page where it's like at the end of the chapter, where it just sort of lists all the terms that you talked about. Another page, but now boundary isn't really in there. So this is the kind of thing that you'd expect from doing this. Now we can change the search term. Let's see. We could change the search term, and now you're going to get, a different set of things. This one's an odd one in that it doesn't have it listed for some reason. Weird. But you get, these are the neural net chapters. So that's just using cosine distance, just comparing the vectors, doing a nearest neighbor. And it actually does a pretty good job on this particular text. I did an SVD dimensionality reduction from the, just like we described in the book. It didn't really do much on this data set. The book is very consistent in the terminology it uses. So when we talk about regression, we always call it regression. When we talk about neural nets, we always call it neural nets. There isn't a lot of synonyms in the book. Where if you went to newspapers, you'd have a lot more, if you took the text of newspapers, you'd have a lot more synonyms in there. There'd be a lot of terms that you could compress using SVD. And so SVD has limited uses if you have very consistent use of your words. It has a lot more functionality when you have a very diverse corpus with lots of different stuff in it. So I didn't actually show the SVD because it didn't really tell us anything. Then I wanted to go and do some clustering on this data set. So I just clustered the data using k-means, and then I basically, well, that's kind of big. I basically grouped them by chapter and just did a histogram of the clusters that the different pages got put in. So for each one of these graphs, it's basically the set of pages in a chapter. Each page got into a cluster, a single cluster, and then this is just the layout. So what we'd like to see is, a given chapter will mostly belong to a single cluster. That's not guaranteed. There's nothing that enforces that, but that's what we kind of would like out of the clustering. So we generally see that. Some of them, like chapter 6, it looks like it fell kind of into 2 clusters, but chapter 2, 3, 4, and 5 are actually pretty clean. They all fell into an individual cluster. Now you will notice like some of them, like 2, 3, 4, and 5, all kind of fell into the same cluster. So that was sort of the classification chapters. I don't think 5 was actually, but it might have still been the classification chapters. So you it would expect that. And then you come to these other chapters, chapter 8, 9, they start having different clusters. So it's kind of interesting to be able to cluster these things just using the vectors. Now in a more diverse corpus, you would probably cluster the projected SVD vectors, not the original word vectors. They'll just be smaller, more compressed, and we'll probably do the clustering A faster and B probably better. So we didn't do that because of the corpus we used, but it's definitely something you would normally do. Then we talked about doing the topic model. Now the topic model we talked about was a fairly simplistic topic model where you created k topics and then each topic had a distribution over words. That's by far the simplest topic model you're likely to run into. It is not the topic model that is in common use. The most common topic model is actually called LDA, and you will find LDA in scikit-learn. You won't find the topic model that we used in scikit-learn, just because it's not the best. And teaching LDA when you want to work through the math is actually really hard. It's got multiple distributions. Any given document actually gets a probability over multiple topics. So you could have a single document that is in topic 3 and 4, and then each topic has a distribution over words. So it's just a generally more difficult thing to do the math to describe it. However, if you need to do topic modeling, generally you're going to use LDA. However, we did the topic modeling here. You could see the same kind of effect that we saw in the clustering, and that's what we kind of expect. The topic modeling is going to do something very similar to the clustering, but in this case, you actually can get the probabilities back of what the words are, and that's something you can get the most common words that come out of a cluster, but you don't really know what the probability of those words are. So we can go down here. And we can actually get the most common words in a given topic. And again, these are going to kind of lay out to be different. I think they actually did a better job than the clustering, but they're going to be different topics. And you can see this is sort of a regression chapter. This is obviously a clustering chapter. This is back when we were probably talking about the covariance matrix and doing sort of principal component analysis. This is probably some neural net stuff. But then we also see the probabilities. So for these words, we could see that this first word has about a 2% chance of being generated. So layer, as we're sampling to create a document, layer has a 2% chance of sampling it. And then image has a 1.5. Images, which probably we could have compressed a little bit, has a 1.2. And it just goes down. And you could actually, if we look at the tail of this, if we flip those, we actually, which I accidentally did first off, and it looked like garbage, as you'd expect, the probabilities are all basically 0. They're like 10 to the negative 20 for the probability of the garbage words happening. Now, they're only garbage words for that topic. They might be useful for a different topic, but for a given, topic 1, there's going to be some words that never occurred in that topic, and those are basically going to get a weight of 0. All right, I actually wrote the topic modeling code. I'm glad we didn't have you do that for an assignment because it's a pain. There's multiple indices you have to go over. Doing it efficiently is actually really hard. So using any kind of vector math is really difficult. So I'm sure you guys you don't know that you're happy, but you will be happy by not getting an assignment like that. That actually was one of the assignments to write that stuff, and it is not informative and it is a pain. Okay, so we were talking about regression. Regression is just the basically fitting a line to data points. So predicting a real value for a given input. So here are 2 examples. Those are actually the bad examples of regression. Here's some decent examples of regression. We have a bunch of data points. We have to fit a line. As we talked about last week, you'll never get a perfect answer. I mean, some data sets maybe you will, but you'll likely never get a perfect answer for no other reason that there's sort of this for any given data, for any given value in the input value, you might actually have multiple y output values. So as long as you have something like that, as long as the independent variable value 5 generates 3 values of y, you're never going to be able to fit a line through that that's going to generate all 3 values. That's just not how regression works. And then we started talking about linear regression, which is a form of regression. It's actually the same form that's shown here, but it only fits a linear system to do the regression. So it's not generating curves. It's not generating anything like that. It's just a linear system for the prediction. So we can go back and lost my marker. All right. Sorry for the bleed through here. Like I said, I'm a little low on paper today. I forgot to grab some more when I came today. So we can look at, this is just a review. We are going to predict y using a linear system, and then we're going to have some noise. That's just the formula we're basically going to use. We're going to learn beta, and then once we learn beta, the prediction is going to be x transpose beta, and we're going to just basically ignore that noise factor. It's there to do the math correctly, but it's not necessary when you actually do the prediction. We never predict the noise. We look at some of the some properties of the noise, but we never actually predict it. This is a. Let me make sure I got everything off this other page. Yeah, this is generally assumed to be a zero mean noise, whatever the noise model is, and that can be zero mean. We can guarantee it's zero mean because if it isn't zero mean, we can just take whatever the mean is, subtract it from the noise, and push it into the prediction. Remember, we set up our predictions so that it doesn't have to cross the origin. We just made sure that we set up our vector to have a 1 at the end. You know, whatever the features are, I'm going to call those f's. Okay, I'm going to call them asterisks because that's kind of mangled. But whatever those features are, we can always add a 1 at the end, and that becomes our new feature vector. And that new feature vector allows us to not cross through the origin. Now, the next step we talked about for basically learning beta is we assumed that this followed a normal, again, zero mean, and some variance. We don't care what that variance is. We just care that it's a normal. From there, we can treat y as a random variable. And we looked at this both ways, but in general, you can look at it as a normal with this mean and that variance. Again, the variance we don't know, don't care. But you can just push this into it. But this becomes a random variable. Now, anytime we have a random variable, we know we can do a maximum likelihood estimate to get a good estimate. We talked about doing a log loss on beta, and this comes out to be 1, and this is just the normal written out. So we get yi, the prediction, times your beta, there's a transpose in there, squared, plus there's some constant that is parameterized by the sigma. This constant we don't care about. It's going to, for a given sigma, it's always the same. We're about to take the derivative of this. Once you take the derivative, it doesn't matter. I actually missed I apologize. I missed a summation there. So we're going to take the derivative of this to get the maximum likelihood. What we end up with is taking the derivative gives you basically 1 over n. Actually, this guy is pushed out there. That's a sigma. And just copying this. It comes out to be that. We set this equal to 0, and we can do the differential and actually get the maximum likelihood. Now what we're going to do is we're going to rewrite this in matrix form. When we rewrite it in matrix form, just to set up the data here, we're going to write y1 down to yn. We're going to write capital X is equal to a matrix where it's each of the data points, which are vectors. We're going to transpose them. Sorry, that's a 1, not an I. Down to the nth. So this is the same y piled up into a vector, and X is the same data matrix that we always consider, where the rows are data points and the columns are features. Then we can rewrite this. I gotta figure out which one I'm rewriting here. We can rewrite this guy up there, which is basically the loss, as this is the log loss basically. Comes out to be y minus x beta transpose y minus x beta. So that basically gets rid of that summation, and when we convert it to the matrix form. And now we'll take the differential of this, and pretty much got that, I think. When we take the differential, we're going to take it with respect to beta, because that's the parameter that we need to find. We end up with basically 2x transpose y minus x beta, and then we take that equal to 0. This 2 can cancel out. We can just get rid of it by dividing by 2, and 0 divided by 2 is 0. And then what we get in the end is x transpose y equals x transpose x beta. So that's the formulation basically of the linear equations to solve for beta, to get the optimal MLE estimate of beta. Now, the x transpose is not necessarily invertible. It's likely not even square. So we can't just take the inverse of x transpose to fix this equation, to make it easier. However, x transpose x, that's definitely square. And except in degenerate cases, it's probably full rank. As long as your input vectors, your input data doesn't have anything that's basically a scaled copy of the input. So if x1 and x4 are just scaled copies of each other, then you won't have a full rank matrix. But that rarely happens. You don't expect it to happen. It's sort of a degenerate case. As long as that doesn't happen, x transpose x actually does have an inverse. So then we can rewrite this to be x transpose x inverse. The inverse just moves this, cancels this, and we put it over on this side. X transpose y. So that is the basically the linear system that you can just multiply out to get your betas. Now we're going to call this a beta hat in general, and I'm actually going to put it on top of all of them. The reason we call it beta hat is it's an estimate of the beta. It's not a true beta. We'll never know what the true beta is. All we can do is get an estimate. If we had a different set of data, if we resampled our data or got a different data set, same distribution, but we resampled somehow, the beta hat would actually change, because if your data changes a little bit, your beta hat changes a little bit. In expectation, you expect all the beta hats to be basically equal to beta, whatever the beta is. But we don't actually know that, so we put a hat on top just to say this is basically an estimate of beta, and to keep track of that. Now, do you have any questions so far? This is just pretty much a rearrangement and the method to solve for the betas. Now, when you do this in practice, or more to the point, when you run sklearn or whatever, you don't solve this. You never solve that particular equation. Generally, with any data set of any size, you're not going to be solving inverses or doing something crazy like that. You'll use some sort of linear algebra package to solve this in some different way. I don't actually know what state of the art is. Certainly, you could do an iterative sort of approach where you're doing the same thing we did for, say, the SVMs, stochastic gradient descent, something like that. But that's just a commentary on how you would solve this. But essentially, if you can calculate this, then calculating the beta hat is trivial. Okay, so moving on, put that over there. So the next question. I'm apparently getting caught on everything today. Not sure why that's happening, but all right, let's try this again. The next thing you really want to talk about is how good are your estimates. So you do this regression, you get a beta. If you have a beta, you can get the predictions for new data points or for the training data points. And one of the questions you want to know is how good is your estimate. So the first thing we're going to do is we're going to calculate something called the residual. So this is just the difference between the prediction and the true estimate from your data. So the true Y from your data versus the prediction. This is called, it's basically the error. It's the difference between the estimate and the true value. But it's often called residual. Anytime you hear residual, it just means the error. So one thing you can look at is the mean squared error. We've calculated this before. Sometimes written M, sometimes written MSE. We just square the errors and divide it by n to get the mean squared error. So the mean squared error is a useful thing to look at. It's especially useful when you are maybe trying different methods of regression on the same data set. Then you can compare the mean squared errors to each other. However, you generally can't use mean squared error across data sets. The mean squared error has a unit attached to it. Y has a unit attached to it. X beta, then has a unit attached to it. Because it has units, the scale is sort of arbitrary for whatever your Y's were. So you can arbitrarily scale this up and down. So you can't use the MSE to compare different tasks, sort of thing. So in some ways, it's a little bit limiting in what you can do. So what we'd really like to have is something that is unitless, something where we can just say this regression was good, this regression was bad. And we're going to actually look at how we can do that. So I'm going to come along here. I'm going to just put down some facts that we know about the error. And these they're all proven in the book, but these all come from just the definition of error and basically doing a little linear algebra to get the different things. So if you take the transpose of the error times the one vector, this is going to be 0. If it wasn't 0, basically we can, then we're not at a minimum. And so we can readjust that error, or we can readjust the beta up or down, in whatever way, so that we get to 0. So this basically is just a fact that comes out from how we did the minimization. Likewise, we can say this. That is just a rewrite of the first equation. We instead of using E, we plop in the definition of E, and then we take the transpose of it. We can take the transpose because E times the one vector is actually a scalar. Because it's a scalar, we can arbitrarily transpose scalars. So we end up with, we do the transpose, we get this, and it's the exact same thing. Another fact that is important, and now we're going to use these later on. I'm not just writing these down for no reason. That one is true. We can just do some more manipulation by basically taking the one above it, moving stuff around, and we can get out that fact. Now for y, we can compute some statistics. One is the mean of y. Sorry, this isn't an equals. That's just the mean of y. And this is the one vector times y over n. So you add up all the y's, you divide by n, you get the mean. That's just a fancy way of writing that. And now we want to talk about the. We can also calculate the mean and variance of this. That's a var. That did not help. We could calculate the mean and variance of the x beta. Same way we could calculate the y. Now we don't actually know the variance of y because remember y has that stochastic process. It has that noise in there. We can calculate the variance of. Sorry, we can't calculate the variance of the prediction easily. We can calculate the variance of y. That's just, those are just numbers. But the predictions are actually hard to. Sorry, the predictions are actually hard to figure out the variance. So this is actually a mistake. So let's ignore that for now. The point here, though, is something that's somewhat important. If you do the math on variance, you can show that, I'm having a little trouble writing today. You can show that the variance of y is equal to the variance of x beta hat plus the variance of the error. And we can actually measure the variance of the error. Sorry, we do know these. I don't know why I'm confused about this today. We can actually measure the variance of the error. And that actually allows us to do a pretty good estimate of that is unitless. So there's an estimate of the goodness of a regression that's called the R-square estimate. We'll put a hat on it because it depends on the beta, but it's just the variance of the prediction versus the variance of y itself. A couple things about this. It is always in the range of 0, 1. If it's close to 1, that means most of the variance of y was explained by the model. So what this is really saying is the ratio of the variance of the prediction versus the ratio of the variance of y. So it's how much of the variance in y is explained by the prediction we generate. If the prediction doesn't really explain the y's, then this will be very low. If the predictions are perfect, exactly what they need to be, then it's explaining all the variance, and there will be it'll be 1. Did you have a question? Okay, cool. So this is useful because it is unitless. That is important. Now we can come and we can look at different regressions on different data sets, and we can say this was a pretty good fit, this was a very poor fit. So if we go to the book here, a couple examples. Where's the plus? These are 2 examples we looked at the other day. Arguably, they're pretty good fits. Not great necessarily, but pretty good. Oh, I should switch that. All right. Much more sense now. Okay, so these are the 2 regressions we did the other day. The R-squares are listed right here. So this has an R-square of 0.87. So that's a pretty good regression. It's not perfect, obviously, but in general, it's pretty good. This one has 0.68. There's a little more error. There's a little more variance that hasn't been explained. So you have a lower R. Now, if you come down to these examples where we had very poor regressions, you'll actually see that this one is about 0.4. So that's a pretty poor regression right there. This one, basically almost none of the variance is explained by the predictions. As you can see, it's just basically a line through a big cloud. It's not really doing much of a prediction there. And so the R value is 0.06, or the R squared value is 0.06. So this is kind of, because it's this unitless thing, you can compare it among different regressions, different tasks, and it's pretty useful to identify things. I'm going to skip the proof of this. It's a pretty useful proof. You should look at it. I'll show you what I'm skipping the proof of. I'm going to skip the proof of this variance equals variance plus error, just because it takes a little time to do. We're getting a little bit behind, but it's worth looking at. It's this pretty common technique where you take the definition of variance and you take basically you take the variance of this. You write out the formulation for variance, expanding all the terms, and you actually get back this definition. That is actually a technique that's used a lot in statistics, where you basically expand out the variance, group terms. Some of the terms fall out to be 0, some of them stay, and you end up with this sort of thing. It's worth looking at in the book, just because it's a technique that is used pretty commonly, but it doesn't really, proving it right now I don't think is that informative. I'd rather get to the stuff that we're going to get to later on today. So let's talk a little bit about how to improve regressions. Now we looked at this one. We looked at this guy, and you can argue that that's an okay regression, but we want to talk about ways to improve it. We also have an example further down in the book. Not that one. Apparently really further down in the book. Oh, there was the proof. Here's a example. This is basically a term versus term, the rank of terms versus the number of times they occur in all the texts that Shakespeare wrote. So this is just like the sort of thing that we drew for the book text, where it's the frequency of terms versus the rank of the terms. If you tried to fit this, it would be a really hard thing to fit. It's just very, it's not linear in any way. So you often can transform your data in some way where it will fit the model better. Or rather, you can make a model that fits the data better. So right here, what we did is we took a log-log transformation. So we transformed the y to be the log of y. We transformed the prediction to be the log of the prediction. The log of the input. And what we get is something that is much more linear in its behavior. And so when we fit a linear regression to this, we could do a pretty good job of fitting that particular regression there. So we'll often do this sort of transformations in order to do various to get the data in a way that you can fit better. So here's another transformation that's pretty common. This one on the left, both of these use a transformation called Box-Cox. Box-Cox is a transformation that basically takes an exponential of the y value. Box-Cox is a technique to find the optimal y value. It has to run through and do basically a bunch of regressions on the same data to find the optimal. That's one of the reasons it generally isn't used that often, because it's fairly expensive to do a bunch of, to fit your data over and over again. But you can see here that if you can pay the computational cost of it, it actually gives you a really nice fit to this particular data set. And arguably, this particular data set, it could do a little better job on also. But like I said, it's a little bit expensive. The formula is right here, where lambda is a parameter that is learned through this Box-Cox methodology. But the y just gets transformed according to this formula. Then you do the regression. And then once you have the prediction, you have to undo that transformation. But that's trivial. You just have to do the math to basically get the prediction. You undo this particular transformation. That's the first way we're going to basically help us fit nonlinear data using a linear method. The next way, and this is, for some reason this is out of order in the book. Let me figure 1111. So this is ways down, I think. Where are we at? 11.6, 11.7, 11.8, 11.9, 11.10, 11.11. Okay, there we are. So before we look at that, remember we have control over our input vector. So our input vector generally we think of as the data, the data features we have, and remember we put a 1 after it. So for the example we're going to look at, it was the length of a fish, basically predicting the weight of a fish. So the independent variable is the length, the weight is the dependent variable, and there's a bit of a curve in there that is causing us a little bit of a problem. Now the original feature vector would be something like length 1. So length and then 1. Now we have control of this feature vector. We can do whatever we want with it. So one thing we can do is add features such as the square of length, and then we'd have 1. We can do that sort of thing, where we take a feature and we start adding its powers. Now, if we do that, we're basically, at some point, hopefully, our prediction is linear in one of these features or a combination of those features. So let's look at that in our example. Here what we have is we have the straight linear one is the really small dots. The quadratic is the longer dots, and then the cubic is the solid line. And what you can see is the linear fits things okay, but not really that well. The quadratic actually fits things really well. This is obviously a very quadratic sort of regression here. The cubic also fits things pretty well, but what you find is that it's actually doing something a little bit odd over in at the edge here. Often if you go too far, if you have too high of a power on your inputs, you're going to get some weird behavior, especially at the edges. But on this right-hand side, what we actually see is where we took it to the power of 10. So we had basically length to the second, length to the third, all the way up to the length to the 10 as our input features. And what you see is that it's actually it can follow the data very well, but it's not really doing a very good job. Especially if you look like down at the bottom here where we don't have a lot of data, it gets this big dip that is obviously a mistake. It's unlikely that, between, 35 and 37 that there's, fish get suddenly heavier and then lighter. This is sort of an overfitting where we've fit to the data too much and we end up getting kind of these undulations in the data fit. And certainly at the top end here, I mean, it's obvious that after you go over a certain length, all of a sudden your weight of your fish doesn't drop. If we kept increasing the power higher and higher, we're actually going to get it so that it can go through every single data point. If you have 100 data points, I believe a power to the 100th will actually be able to fit every single one. It can ace everything. But it does it by doing these huge undulations. So things that aren't a data point actually end up completely wrong. So you got to be careful when you use this technique. You really want to limit the powers that you use. From a practical matter, there's also a problem with just scaling. If we have two features, let's say we have, let's flip this back. We'll often do something like this. If our original vector was length and weight, now this is obviously a different task. If we had two features like this, some of the things we can do is we can do length squared, WW squared at 1. But then you'll often introduce cross products. This is a really common technique where you will do something like maybe you do length, width, and then length times width as an input feature. And that's a cross. It's often called a cross. That allows for some interaction features, basically. If there's some sort of behavior where you need to know both of those in order to make the prediction, where there's some dependence on each other, those crosses will allow you to do that. Of course, if you have 100 features and you try to cross them, you're going to get 10,000 features. So this stuff is limited on what you can do. And from a practical point of view, it allows linear functions to fit data that is nonlinear, but you have to sometimes have some knowledge of the problem in order to choose the right combinations. This is definitely true when you start doing a lot of crosses. You don't just cross everything with everything. you end up doing some very limited things where you say, I know something about this problem, I know these two things probably interact in some way, or these three things interact in some way, and I'm going to create the interaction. But that's the only time you do it. Any questions on that? All right, cool. All right, so one of the things we really want to know is how well we're doing with, before I say that, the next thing we really want to look at is outliers. So let me motivate this. Wait a second, what's the figure number? Number 6. 4, 5, 6, 6, 6. There we go. Okay, so one of the problems we have with regression, and actually classification too, any task we do with machine learning, is the presence of outliers. Outliers are basically data points that in some way are different than the other data points. And they really can wreak havoc on your predictions. This is some synthetic data, just some function. It's a linear function with a little noise introduced. And what we can see is that we can actually do the regression, a linear regression that's pretty good. Oh, you guys, you got to yell at me here. All right, try this again. This is some synthetic data. You can actually see that we set it up so you can actually do the prediction pretty well. It predicts the data fairly accurately. Now, an outlier is something where it's just weird. And this one, sorry, no, this is the original data point. This is an outlier. This is a data point that we added just to see the effect of having one bad data point. And you can see that this would have been the original line, but adding one bad data point really skews what that prediction is. So now this is a very poor prediction, the second one, for basically all of the data points. The reason this happens so dramatically is if you look at the loss function, we have a square in there. So when you have a data point that's really far off the mean of the prediction, and you take the error and you square it, that square generates a lot of error. Whereas if you have a bunch of points that are much nearer and you square them, you're not generating nearly as much error. So if you look at this graph, basically if you took the square of all this error up till ignoring this data point down here, that's essentially equivalent to the square of this error for the single data point. So that's why this skews so much. A squared error that we used to actually optimize this, to find the minimum, actually performs very poorly in the presence of outliers. So what we really need is we need some way to handle outliers. So what the process is going to be is we're going to try to identify outliers, and then once we find those outliers, we're probably going to try to just train without them. Outliers are a big problem when you have big data sets. It's really hard to find outliers. It's very computationally inefficient to find outliers. The outliers may not even be so much bad data points as just odd ones. They could be errors in sort of what data you collected, but they also could just be a fish that for some reason for a given length ate too much and got really fat. If you have this giant fish, he'll be an outlier. That's definitely possible. It's just the way that the data could fall out. Now, if you have that fish in your data set, it'll throw off all the other predictions. So you still might want to get rid of that particular fish in order to get your prediction, get your sort of the mean prediction to be better for all the other data points. So the question here really is going to be, how do we identify the bad data points? Might have enough paper. Let's do this. So the first thing we're going to do is we're going to look at something called the hat matrix. The hat matrix is going to be defined as, if we take our beta, we're going to take our formula for figuring out our beta, which was x transpose x inverse times x transpose times y. That is just the linear system that you use to solve for beta hat. This particular thing is called the hat matrix. The hat matrix is kind of an interesting thing. The first thing to notice about the hat matrix is this is just a matrix that basically is saying that each of the, where is this? I totally wrote the wrong thing here. This is x beta. That's your prediction. Sorry. Let me make sure I get the rest of it right. Nope, I didn't. Have to add an x there too. That comes directly from the definition. I just wrote the wrong one down. I had 2 lines in my notes. So that's the hat matrix. So the hat matrix is interesting because the first thing you should notice is that this is a matrix that basically says our prediction, the x beta hat, is equal to some linear combination of the original inputs, the original y's. So to get the new prediction, you basically have this matrix that says take all of the old predictions, the original values, add up some amount of them, and that will spit out a new prediction. Some of the interesting things about the hat matrix, and these are very strange for matrices, is that the hat matrix times itself equals the hat matrix. It's just if you put these two things next to each other, everything cancels out and you get the same thing back. The eigenvalues are either 1 or 0, which is very odd. You definitely don't get many matrices like that. It's obviously symmetric. And the most interesting thing is if you take the ith jth entry, so we're going to do lower, not having a lot of luck today. Ith jth entry, we're just going to do lowercase. And you go over the columns and you take the square of these, they're always less than 1. So if you take the square of a column from the hat matrix and sum it all up, they're always less than 1. And what this really means, remember, like we said, that we're really talking about the prediction is a linear combination of the initial y's. Now, if an entry in this hat matrix for a given column, which corresponds to a given prediction of a y, if it's really large, let's say you had an Hij of 1. If that's a 1, that means that the Hij's, the other Hij's in that column, have to be 0. Because 1 squared is 1, and so that implies that all the other ones are 0. But if Hij is equal to 1, that means that we predicted something based basically on the input. So we took an input and we just sort of copied it through and generated the output. That's generally a bad thing. That's just memorizing that particular point. It's not building some linear combination of the data to generate the prediction. It's just grabbing one of the points and passing it through. That's generally not going to lead to a good regression. So basically, the first technique we're going to have for identifying outliers is to look for elements of the hat matrix where where any of these are really high, but more specifically that the diagonal HII is a very high value. If that is a high value up towards 1, that means that you're just predicting your input and you're basically not learning that point very well. This, the hat matrix, there's no cutoff where you can say, yes, this is a good one or this is a bad one. Rule of thumb, anything bigger than, say, 0.1 in the hat matrix probably is an issue. It's not guaranteed. It depends on your data set. But anything where it's greater than 0.1, you're probably saying, yeah, there's something wrong with that. Certainly if you're getting up to 0.5s, 0.9s, your regression, there's something wrong with that point in your regression. And it shouldn't be like that. This, by the way, is called the leverage, or the leverage, depending on whether you're British or not. That's the term for that particular form of identifying outliers. The next thing that we're going to talk about is called the Cook's distance. The Cook's distance is basically what we're going to do is it's a procedure where we're going to walk through the data and we're going to drop one data point at a time and see what happens to the regression and how the error changes, basically. So if y hat is your prediction, in the book he calls it y with a superscript of pred. I'm not sure why he does that. Y hat is just as informative. But if this is your prediction, we can talk about a prediction where you drop a data point. And this is how we're going to write the same linear prediction, but we train the regression without a data point I. So it's basically the same system missing one data point. And when you trained it, not when you're predicting, but when you actually trained it. Then we can look at the difference between these two things. And we can square it because we square everything in here to find the difference. And then we can normalize it by the, this is actually the mean squared error. This is the dimension of your input vector. That normalization factor doesn't really matter. It just gives you a number. You're generally not going to compare Cook distances between different problems. So it doesn't really matter what these normalizations are. However, if you do certain normalizations, you can do some statistical analysis. We're not going to talk about that. It gets pretty complicated. But you can definitely do this if you do this sort of thing. Again, this is the sort of thing where anytime it gets kind of high, then you might have a problem with that particular data point. How are we doing? Oh, we're out of time. Okay, well, we're out of time. So we will continue on this. There's one more thing that we'll look at next week, and then we'll look at some graphs of how to actually look for outliers. So I will see you guys on Thursday.